Log on, tune in, find out. Another good idea from Cambridge.
Have a long-standing relationship, including a shared fascination with the golden ratio, which was known to the ancient Egyptians as well as the ancient Greeks. So it's very exciting to be hearing today about the link between art and string theory, one of the hottest topics in applied mathematics today. Before introducing our speakers, let me tell you a little more about the Newton Institute. Based in Cambridge, the Newton Institute is a national facility that supports mathematical research throughout the UK. It's funded by the research councils with contributions from the London Mathematical Society and other charitable trusts. Although its role is a national one, it receives very significant support, both financial and practical, from the University of Cambridge, and for that we are all grateful. In addition, it has a development board of lay supporters who fundraise in the city and elsewhere to ensure the continuation of high-level research in what is an uncertain future of funding, in terms of funding, from public sources. We may be biased, but we think that this is a very special building. The Institute is part of CMS, Cambridge's Centre for Mathematical Sciences, and some of you been in this part of the world before might have noticed in particular the core building, which has a lawn on its roof, not to mention daffodils. This building was purpose-built with a creative space that you would have noticed that's designed to nurture both individual and collaborative research. It has in excess of 140 square metres of blackboards. That's quite a lot. And you might have noticed the Turing machine on loan to us on display in the lobby. Please look at it afterwards. A landmark in the history of the Institute was the announcement in this very room by Sir Andrew Wiles of his strategy for successfully proving Fermat's last theorem, a problem which had been an open question in number theory for 350 years. Before I introduce our speakers, let me get a couple of practical matters out of the way. First of all, the fire alarm. If the alarm sounds, please vacate the building as swiftly as possible and congregate in the car park beside the main building. And second, and this is very important, mobile phones. Please turn off your mobile phones now. Even in silent standby mode, they interfere with our audio-visual equipment, and they will cause a buzzing sound which will be streamed live to the world and recorded for posterity. So without further ado, I would like to introduce our two speakers today. Professor Grenville Davey is a renowned English sculptor, famous not least for winning the 1992 Turner Prize, but of course you all knew that already. We are delighted that Grenville agreed to be the first artist in residence at the Newton Institute. And we found it fascinating how the ideas behind string theory, one of the current programs, have inspired and influenced his recent work. Dr. David Berman is a reader in physics at Queen Mary College at the University of London, and he is an expert on M theory, which is an extension of string theory, and he is currently organising a programme at the Institute on mathematics and applications of branes in string and M theory. The format of this evening's event is as follows. David will talk to us for approximately half an hour about string theory, and then Grenville will talk to us for a further 15 minutes or so about his work. Finally, there will be a question and answer session before a drinks reception in the main lobby. So I just, without further ado, like to hand you over to David.
Okay, can you hear me?
Yes. Very good. Okay. So, what we have up here on the screen are some strings. And eventually I'll get to string theory. But before I do that, what I want to talk to you about is what theoretical physics is. And in fact, what I'm going to tell you is that theoretical physics is a search for unity. So I'm going to have to tell you what I mean by unity. And then I'm going to digress. I'm going to tell you about two of perhaps the 20th century's great insights into theoretical physics, Einstein's general relativity and quantum mechanics. So very rapidly, you'll be catching up with the current state of the art in theoretical physics. Then we're going to go back to this idea of unity and unification. And combining these two things of quantum mechanics and relativity, we'll see that there is something wrong with the current way in which we view the world and why we need something called string theory. And finally, after all of that, you'll then learn about how once you've been converted to string theory, you'll decide that the world will be a very different place. And I'll talk a bit about the different ways in which we understand the world changes once we accept the idea of strings. So let's begin with some history. In some sense, here in Cambridge, Newton unified gravity. And what do I mean by that? It's a very simple idea. You see, we're used to the idea that gravity is one force and it explains stuff, why things fall down, the motion of the planets. But you see, that's the sort of remarkable thing, that there is one equation, and that one equation basically tells us why things fall down here, and it tells us why the moon goes around the Earth, and it tells us why the tides are there, and it tells us why the Earth goes around the sun. So with that one single equation, you explain a whole multitude of phenomena that appear very different. And we take it for granted now that gravity is one thing, but if you think about it, that phenomena of the tides, the motion of the planets, the fact that things fall down locally, are all very different. So what unity is a single explanation for many different things. I thought I should throw in some art quotes. Well, this is one from Picasso. A painter should work with as fewer elements as possible. And so should physicists. And that's the point of unity. You're searching always for the minimal set of things to describe as much as possible. So I guess after Newton, the next big step forward was by Faraday and Maxwell. And Faraday was the guy who really did the experiments and saw all the different phenomena in electromagnetism. And if you think about it, they are very different. We have static electricity, we have magnetism, and then what was remarkable and what Maxwell did is through combining electricity and magnetism into one thing, so they became different manifestations of a single force called electromagnetism, there was a prediction. And that prediction was that there should be electromagnetic waves. And the electromagnetic waves he predicted are the things that you're all familiar with. It's light. Maxwell predicted light just from saying we should combine and unify. So now we're moving up to almost the present day, 1979, Weinberg and Salam. I love this picture of Steve Weinberg. He looks so contemplative. This is from their Nobel Prize pictures. What they did was to unify electromagnetism with the nuclear force. To be precise, the weak nuclear force, which is responsible for the decay of atoms and radiation. And this is something which people are less familiar with. We're all familiar with electromagnetism, it's sort of the same thing. But what they showed is actually electromagnetism and the force which causes radioactive decay are also different aspects of the same single force called the weak nuclear force. So, seemingly different forces in nature appeared as different aspects of a single force. But there were two things left. There was gravity, that wasn't combined with this electroweak force, and there was a strong nuclear force, which is the thing which sort of held quarks together in an atom. So there were two exceptions there, but in the end, though, that was pretty good. So that was all the forces in nature had been combined into electroweak gravity, and the strong nuclear force. So, if you think about it, all of the phenomena that exist in the world and in the whole universe, it's sort of remarkable that there are only 3 forces that we've ever seen, when you think of the great diversity of things that happen. So that's okay for forces. But what about matter? This stuff, glasses, whatever. So the Greeks already had the idea of unification with the idea of reductionism. That as you went smaller and smaller, you had more and more basic building blocks that could actually be simpler and simpler. So indeed, as you go down from our man to molecules, to atoms, to nuclei, to quarks, all of the stuff in the universe was made of a very small number of elementary particles. And this is the current, what's called standard model. We have 6 quarks, 6 leptons, and 3 types of force. And I say again, I mean, this is everything in the universe. It comes down to that, according to our current state of knowledge. It's not a lot of stuff in some way. Given the great diversity of nature, it's incredibly basic. So it's quite good, but unity means one. You want to do better. We don't want 3 types of force, we want 1 type of force. We don't want, however many that is, 12 types of matter things. We want 1 type of matter thing. And even better, we don't want to have even a difference between force and matter. So can we do better? Before I go into that, let me tell you a little bit, just for a minute, because it's very impressive how we know these things. So this is a picture of CERN, where they do these experiments and test the standard model of particle physics. And through collisions, so this is, I should explain a little bit about this. This is a map of the French-Swiss border. This little dotted line is in fact the border between France and Switzerland. This is Geneva Airport. And this is a sort of a schematic of the ring, which is actually underground, of the particle accelerator that collides together particles and gives you a way of probing into what the basic building blocks of what nature is made of. And then at these points here, you have collisions and detectors. So that's the actual tunnel. This is the vacuum tube, and then the electrons, well, now protons, are accelerated along this tunnel. If the proton was static here, it is given enough energy in moving from here to move at 99% the speed of light. Where does all the energy go as it gets more and more accelerated then? It goes into the mass and the energy of the particle as it approaches the speed of light. When these things collide, they are basically concentrating huge quantities of energy in very small spaces and using that to probe nature at these very small scales. And this is just some impressive bits of machinery that my experimental colleagues play with. Now, so we have this description of nature. And it's based on this experimental data of particle physics. But we want to do better. And string theory was the idea of how you can do better. So what can you do? And this is where there's something about how theoretical physics works that's, I think, quite revealing. You take a step back and you say, what have I always assumed physics to be like that I can change? What was somehow always in the back of my mind that I took to be true that may not be so? And what string theory does is say that those basic building blocks that in some sense the Greeks gave you in their notion of an atom don't have to be point-like. When you were taught science in school and you opened a book and it had a picture of an atom and there was an electron and other stuff, they were points in that book. The electron was typically yellow, the proton was red or black and so on, and these were little spheres. And that was a very nice Greek idea and everything was lovely, and then you went through the rest of your life thinking that all elementary building blocks are points. why does it have to be so? So what string theorists did was take a step back and say, what if the basic building blocks are not points, but strings, have extension? Strings have one very distinct advantage, that they can vibrate. A particle just is, its properties is given, are given. And it can just move about, and that's it. It is what it is. A string, however, can vibrate, and it can vibrate in different ways. And one of the great richness of string theory is that how it vibrates corresponds to the perceived properties that we have when we think it's a particle. So the standard question is, how long is a piece of string? And in current viewpoint, those basic building blocks will be 10 to the minus 34 meters, which translated in less technical terms is very, very small. And you see, it had to be very, very small because in the end, there's a reason why we had the intuition that elementary particles should be point-like, is because when we look at them, they look like points. But if you take a tiny loop of string, a circle, that's of this length, how could you distinguish it from a point? Unless you could really resolve to those distances. So now I've told you about some of the basic reasons why you might think string theory would be a good idea. Postulate that the basic building blocks are extended. Let's move on very quickly to some other ideas. And then we'll see why we might need that idea of string theory as an extended object. So, now you're going to learn about general relativity. And it's a unification game again. So the first thing which Einstein did was unify two things which you've gone through life thinking are separate. He unified space and time. Your conscious mind deals with space and time very differently, but if you think about it in terms of physics, space and time are really quite similar. So Einstein freed himself from his psychological perception of space and time and wrote down the laws of physics treating space and time on an equal footing. So that was the first trick, unify space and time. The second trick was really clever. He then postulated that space and time could bend, stretch. We're used to the fact that space might stretch. Think of a rubber sheet. We have some rubber sheet. It's space. We have some geometry on this thing. I can pull it. I can stretch it. That may be not the fundamental space that we're used to, but we're used to a geometry that can be malleable and stretch. Einstein said that stretching and bending can happen to the fabric of space itself. Well, that's a bit of a leap. But then he made a prediction, which is that that causes gravity. And the remarkable thing is, very soon afterwards, it was tested. The stretching and bending of space and time leads to the bending of light in space. This was the first reported measurement of that by Eddington. And it causes even the dilation of time clocks. And this is a map of GPS satellites which rely on, in fact, correct understanding of general relativity to get the GPS system to work. So, that was a 2-minute review of relativity. It is the bending and stretching of space and time. So when you leave tonight and says, what did you learn? And then over canapes and cocktails, you can say, I learned that gravity is the bending and stretching of space and time. But now you're going to learn about quantum mechanics. Quantum mechanics is about many things, but there's one aspect I want to focus on. And it comes down again about this thing that's somehow in the back of your mind that you always assumed to be true when you were taught physics at school. When you're given the laws of physics, you tend to think it doesn't matter about the size of things. And indeed, Newton's laws don't, in the sense that you have the same law for a planet as for an apple. And then you imagine, because of your human experience, you don't deal in vastly different scales. We don't deal in our everyday world, our common sense perceptions, with the incredibly small atomic scale and the cosmic scale at the same time. We're tied to a scale of about human size. What quantum mechanics tells you, one of the many things, is that size matters in physics. The laws of physics depend on the scale in which you examine things. And it tells you something more. It tells you that the smaller scales you go, the more random and non-intuitive things get. So people will tell you all sorts of things about probabilities in quantum mechanics, about this, that, and the other. And it all sounds weird and crazy. The reason for that is that those things, that quantum realm, becomes very important when you're at the small scale. And the smaller you go, the more those quantum effects are important. Okay. Are we happy with quantum mechanics? I've got people nodding. If only my undergraduates at Queen Mary were so happy with my lectures as you are tonight. So, you have now done a crash course in theoretical physics. You've learnt that you need to unify things. That's what you have to do. You have learnt about general relativity, that space and time bend and stretch. You've learnt that if you go smaller, things get random. So now you need to unify those ideas of general relativity and quantum mechanics. So, if this sheet is our depiction of space and time, and we zoom in, I'm zooming in, and I go deeper and deeper and look at its structure, when I reach some quantum scale where quantum mechanics comes into point, I get fluctuations. Small fluctuations at first. But then as I zoom in ever deeper, further and further, what quantum mechanics will tell you is that the structure of space and time will become more and more random and effectively tear itself apart. Which sounds like a ridiculous episode of Star Trek. But I want to emphasize that this is combining two things which you know have been experimentally verified and well understood, general relativity and quantum mechanics. And you combine those two things, and when you do so, you produce something which is nonsensical, which is that space-time at the very smallest scales becomes, well, nonsensical. So, we go back, and you've now been trained how to think. What is it that you're assuming in the back of your mind that you always held to be true that you must abandon? So I'm saying I can zoom in smaller and smaller. I'm saying that you can never stop me examining nature at smaller and smaller distances. Maybe you can't. And you see, this is the solution that string theory gives you. String theory provides for you the shortest distance in nature. If everything in nature is built out of these strings, and the strings have a length, albeit a very, very small length, there is a point where you cannot go any smaller. You can't go smaller than the strings themselves. In this sense, string theory is pointless. There are no points in string theory. There are only things of finite size. And it's like your TV. When you look on your TV, far away, everything looks smooth and beautiful and fine. When you go right up to it, and you start to then resolve the tiny pixels, you see at that tiny scale that it doesn't go infinitely fine, there is a shortest distance there, the size of the pixel. In some vague way, the string gives you the size of the pixel of nature itself. So when I go to smaller and smaller distances, I'm rescued from this quantum problem via the existence of the string. Now, you see, if that was the only bit, string theory would not be contentious. However, string theory does something a bit more. So it unifies quantum mechanics and gravity. But I said when Maxwell unified electromagnetism, there were some predictions that you didn't expect. In Maxwell's case, he predicted light. It was a natural consequence. The surprising natural consequence of string theory in combining quantum mechanics and general relativity is that we live in more dimensions than we first might imagine. String theory makes a prediction that we live in 10 dimensions. So the first thing to realize is it's the only theory that makes a prediction of the number of dimensions we live in. And if you think about it, when you were first taught physics or maths, why did you not go, "Excuse me, sir, how come we only live in 3 dimensions?" It's all very well to talk about the physics of this, that, and the other, but that physics lives in a certain number of dimensions. So string theory gives you an answer. It just gives you 10. So you might be worried. Don't worry. Already, back in, beginning of the 20th century, Kaluza and Klein, very shortly after general relativity, had a quite remarkable idea. So, if this is my space-time, it can bend and stretch. They said, well, if it can bend and stretch, can't it just go over and form a loop and join back on itself into a circle? If I'm allowed to do this, why aren't I allowed to really join it up? And actually have spaces in space and time that are circles. Of course, if you went in that direction, you would just come back on yourself. And then they said, but the circle could be very, very small. This is where one of those magicians that does this and then pulls out the great puncher. If you make this very, very small, from far away, this will look like a line. I will lose the fact that it was ever a sheet of paper. If I shrink this up really small, it will look like a line. So what their idea was that actually you could have extra dimensions in nature, and they will be like circles, but very, very small circles. So they already had that idea back in basically 1920 something. People thought they were mad. Einstein said, don't publish this, you'll start raving mad. There's no way we live in extra dimensions, why would you do that? They did make one extra prediction though, which is that actually this also produces electromagnetism. So gravity in 5 dimensions is actually looks like gravity and electromagnetism in 4. So when string theory had these extra dimensions, then the answer was already given by Kaluza-Klein. Only now you don't just have simple circles, you have extra dimensions which take on very complicated geometric forms, which are the subject of mathematical study, that would actually be 6-dimensional, very, very small surfaces. Okay. I've never been able to come up with a public way of explaining why 10 dimensions. I have tried deeply and profoundly. But perhaps it's worth a comment of why we are in a maths institute. Maths is exceedingly powerful. That mathematical consistency of how string theory works gives you answers like this. And although I can do very hand-wavy things to explain most things, I don't have a way of doing it. So I'm sorry, you'll have to trust me. Let me move on to one thing before we can move on to Grenbel's work and how we ended up working together. So that was about unity, explaining different stuff with one thing. That was always the goal. The surprises, one of the surprises of string theory is that it also provides something called duality, where you can describe one thing in different ways. It's the opposite of unity. But the surprises is that the fact that there is one thing that is the same is a surprise. That sounds very unclear. So let me give an example. So there is something called T-duality in string theory. So I had this example of a Kaluza-Klein circle. This was a circle in space and time that was very small, of radius r, length r. And then the weird thing is, according to how the dynamics of how strings see the space, they're not points. They don't see the space like points, like you or I see the space. They see it differently. And to a string, there is no difference between a circle of radius r and a circle of radius as 1 over r. The two are dual descriptions. When we just say that is a circle of radius r, to a string it's the same thing as saying that's a circle of radius 1 over r. You see, that's the weird thing. When you abandon the idea of points in geometry, and then you have everything explored by things like strings, then you get these very strange connections between things. So usual geometry becomes then ambiguous, with seemingly different geometries being just like a different point of view of the same object. So I'll end with this thing. This is where I will say there is a relation to art in some sense. Apart from describing nature, which is what we want to do, it fundamentally challenges the way we view the world. So I apologize if my exposition tonight has been, well, a lot of long words and a lot of gee whiz. But in the end, you know, you sort of come away and think, yes, one has to sort of step back. And what have I been assuming about how nature works? What is it that people always assume to be true that they change, that gives us these insights into things? It also has this weirdly deeply aesthetic feel. As soon as you've got a unified description, there's something that makes you think, wow. And it's hard to put your finger on, but there is this deep aesthetics which people feel when you're working on things like this. And finally, I'd say it's been a core part of human society and culture forever. And that's something that we should be proud of. And in a current funding climate where they want to tell you we'll only fund you if you make money, that's forgetting the things that made us human and why you've turned out tonight, is that describing nature, challenging the way that we see nature, is a fundamental part of humanity. Thank you.
Okay. Hello. First thing, I've got a lot of pictures to look at and they've all got information attached to them, so I won't talk about individual works. If you want to ask after, please do. Firstly, I'm really glad that these things got a mention. They are green boards or black boards, I'm not sure, but this is the closest I've been to them so far. And it was an amazing thing to come here the first time and see them everywhere. It's such a fast way of drawing. Okay. There's been one really consistent thread throughout my practice. These images represent about 25 years, and that is the business of making pairs of objects. I call them objects, but they're sculpture. The other pairing I found from the outset was that these are partly fabricated, partly found. So they exist as found objects and fabricated objects. What's happened recently, since I've been working with David, is this relationship with drawing. I've drawn or made drawings consistently throughout my time as an artist, and I'm beginning to realise that understanding that I can either draw retrospectively, draw to sort out problems. I think the other aspect to my practice also is that what you don't see and what's actually present in the studio are often what seems to be a kind of appropriate number of works in progress. This is a kind of invented number for me, usually around 6, maybe 5, maybe 7. But these are things that are on the go and have a relationship which is kind of left behind when the work ends up out in the world. The other pairing, if you like, often these pictures actually tell you a different story about the work. They are actually basically drenched in cellulose paint, so they're not your Mercedes, they're your lollipop, okay? The insides are often raw, and the external surface is either sealed or treated. They are, as they were described once, largely circular, and my preoccupation with the circle, as I guess in a kind of painterly way, I would fabricate maybe a dozen circles of different dimensions and use them as a stretcher. Okay, so all these things have a kind of acoustic, like an acoustic event. They all have volume. They're all sealed. The earlier works were particularly sealed. You will see some evidence of human scale, finger holes, perforated surfaces. So at some point I decided to kind of let the air out of them. Okay, I think my relationship to drawing was quite oblique, I think, in the early days. I used to try and resolve problems, and I started to understand what the relationship is to making. A lot of these are unstable. I would describe them as unstable. This one particularly is inverted. And I think the change in the relationship to drawing was that I started to draw on the surface and use a fluid surface rather than a plasticide surface. Okay. What's common is that I really basically started out by finding failed fabricated spinnings. So nothing I ever used was perfect. Everything was either egg-shaped or basically skip-based. Okay. I did, in a couple of these works, ask fabricators to remake the mistake, okay, which caused a lot of fun for a lot of people. Basically, I hope that there are some aspects to them which I can place, or some sense of them which is like a celebration of objects that already exist in the world. There are references you'd see. There's some very odd kind of basic science going on there. All right. The relationship to the body is crucial. What I wanted to examine was the notion that they may, or their relationship to the viewer or the space has to be clarified. Installation, is that? Yeah, that's right. That's okay. That's it. The installation of a number of things in space, a gallery space or in a public space, is always seen to be a crucial issue. So the relationship between a group of objects has always been primary. Excuse me. At this point, what's interesting for me is I start working in a gallery environment, start working in a public realm. Okay, over a period of about 15 years, every object I ever made seemed to end up in a gallery, and I was at one surprising point given the opportunity to work outside of the gallery. And up until 2008, that's all I did. Very much relationship to the body, very much a kind of conundrum. The work in the public space was often about time and waiting with the work, being with the work, physical quality of the work, the public or the body's relationship to it, and in a bigger picture, an overall or broader design concept. So I think in about 2008, I had the chance to go back into what was a difficult gallery space in Canary Wharf, and there's some things that illustrate that. Okay. Excuse me. I think what David was saying about the idea about unifying, is that a drive behind making pairs or inventing pairs of things? I think it is a kind of closer examination of relationships. I think all of these objects, as I said, are slightly flawed in that they were never intended to be perfectly fabricated or perfectly formed. This particular print, my interest with the glass eye, I don't know if you've ever felt one, as an object that doesn't seem to contain any light but reflects light. is a smudge on your thumb. The bottle stopper contains light and is a kind of drawing of an eye, okay, if you understand what that means. These are just some working drawings, okay. None of these drawings I've selected could ever be made, or I wouldn't actually really desire to make them. There's a whole new thread to the work. Excuse me. Okay. So I'm waiting to get to another work. In terms of these drawings, I'd like to. I don't know if you know the artist Richard Deacon. Richard Deacon made a great statement once that a lot of the radius is in his drawings. A lot of the drawings that he uses in terms of making sculpture are reflected buildings. He used an example of a reflected building, a building reflected into the surface of a car, or the polished surface of a car. Okay, so that's his source. My surfaces are absorbent, super absorbent surfaces. I'd like to think that there was some way that I could find a way to use the third partner, if you like, if that's the right way of putting it, in this kind of equation. I haven't achieved it yet. David talked about the scale. I think that's primary. There's a kind of sense to the scale in terms of the body. This is a great one. This is Chelmsford. If you ever get a chance to go to Chelmsford. All right. These are kind of plus and minus lifts, all right? And the thing is, getting into a lift is often an event, but not in County Hall in Chelmsford, because people enter from the back. Right? So what you get is this kind of checks and balances with plus and minus on the top. I will tell you about this one. This is in a formal setting in a palace in Jiangsu province, in Jiangsu. And I had an aside, it was like that third number, with the guy with me told me that one of the two panels that introduced the family to the guests was leave your anxiety at the door, okay? And the lovely thing about that, by the way, is that that's been in lots of wedding photographs. It just happens to be outside the registry office, okay? So the first time I went back to look at the work, it was covered in confetti, and just about every time I've been back to see the work, it's been covered in confetti. All right, so it stopped again.
Sorry about that.
That's okay. All right, so what I want basically for these things to be is a celebration of a relationship with other objects in the world. That's always been primary to me. It's an examination of some aspects of things we understand, some aspects of things we observe. I'm very much in the kind of spirit of Oldenburg, I guess, from a very early age. Not in terms of what the work is like, but what the spirit of the relationship is. Excuse me. This title, Leap Second, I think more in terms of I love you so much, so I'll let you jump first. A lot of these titles are jokey, or slightly jokey. Okay. The house basically relates to the target, which is the target for curling. I understand. It's a fascinating game. I don't understand it, but I love the idea of a target being a kind of destination. So I'm waiting for one object. Okay, this is basically a 10-year project. It's a repeated waveform etched into copper. There's, as you might have seen or likely to see, there's a repeated wave pattern on ceramic tiles. I think it was about this time that I got into the idea of multiples. And as an artist, you can get the opportunity, like in the same sense as working with printmakers, to make multiples. These are factory-made objects. Again, I think, like with Randall Page, there's an element, I think he said that some aspect of the material or some aspect of the work can be taken out of your hands, and that's a pleasurable experience. You don't necessarily have to identify it accurately, but there is this thing that you can take some things or some part of your practice outside of yourself. So currently, this is the final slide. I'm working on a multiple project for the Olympic Park, which is 64 castings of fingerprints. And these again are their very large fingerprints and very small fingerprints. 91 metre long wall. I guess I'm making groups of pairs. Okay, I think that's just about it. Thank you.
Well, I'm sure that you will all agree that those were two truly fascinating and stimulating talks from both ends of the spectrum, but that really spoke to each other. And I'm sure that you have a lot of questions for David and Grenville. So would anyone like to kick off with a question? String theory or art?
Both, if you like.
Both if you like. Yes, at the back.
With quantum entanglement,
Oh, could you speak up, please? Sorry.
Oh, sorry. With quantum entanglement, isn't that like instantaneous action at a distance?
Okay, good. You might think so, but not, for the following reason. So for those of you who don't know, quantum entanglement is the fact that two things can be correlated or entangled. So some measurement here can influence a measurement far away. So and when I say far away, in principle, the other end of the universe. So then you can say, well, why is that not action at a distance? And it's not action at a distance because I can't use that entanglement to communicate. Although the result is entangled, is correlated, I can't use that to influence far away. Okay? So for action at a distance, I have to do something here, and then I control what happens very far away. And I can't use entanglement to do that. I'll do something here, and something far away will be affected, but through the randomness of quantum mechanics, I can't use it to control the thing far away.
Any more questions? Yes.
There's so many different things I could say, but I think what comes to mind, to be honest, is with this art of yours, you know, I don't know much about art, but I know what I like. But in some cases, it seems to me, you know, where it says against a stone pillar or in nature, I can't wait for it to rust away. You know, I mean, do you mind if we dislike it? That's, I think,
No, not at all. No, you get used to that. You can't like everything all the time. Things do rust away. Things have, in fact, there's a move or has been a move to decommission objects that are in public.
Just trying to be honest, you know.
No, it's been taken on board. There's a decommissioning process.
Also, when you started talking, sorry to can't go on, but when you started talking about gravity in the very first place, you sort of said Newton gave us an explanation of why things happen. But I'm not sure that's really true. He didn't really, the why is the...
I don't think I used the word why.
Oh, you did. Definitely.
If I did, I'll take it back. Because I agree. He gave you a description. I absolutely agree there's no why. I don't think we ever answer a why question, really. We describe things. What's remarkable is that we can describe things with less and less.
Yes. Hi, I wondered, David and Grenville, you guys talked a little bit about how you work within your individual disciplines. Could you tell us a little bit about the process of actually working together? How do you actually do it?
We meet. David comes around and breaks things in my studio.
Yeah, that's mostly what I do.
Which, no, I don't mean that. Intentionally sets out to break things for a reason. I try to take things on. It's an immensely complex area, but some of what's here I've got to, and is like basic to something it's been a preoccupation of mine. So I'm trying to negotiate that and find a place for it to live. So I make things.
Yeah, I mean, I think what I learned from working with Grenville was when I first started this, I thought I had all these ideas and then it would happen. And then I learned to look at what Grenville does, and you have some concepts that you want us to share, but then in the end what Grenville was talking to you make an object, and then it lives and dies by its own aesthetic quality. And then, so we've been through an exploration. I talk a lot to Grenville. He listens, hopefully, and then he builds stuff, and then I look. And I don't prejudge it based on whether it fits into what I originally said or not, but based on what it is itself.
Yes, please.
If we do not find the Higgs particle this year, does it have any consequences for string theory, and if it's, does it verify it or?
Okay. If we don't find the Higgs particle, well, first of all, I would say it's unlikely we'll find it this year, because in order to really have a discovery, we need the statistics to go much further, and I think they would even only expect that to happen in 2 years' time, to be really certain. The implications for string theory are very unclear, in the sense that string theory could accommodate the Higgs and expects to have a Higgs. If no Higgs is found, I can imagine that string theory could accommodate that too. What I would say is that if they find superparticles, which there's a reasonable chance they will do over the next few years, then that would be a great experimental encouragement for string theory. Yeah. So I think the Higgs isn't going to do as much good, but I think anything to do with supersymmetry would be very, very important.
Well, I'm glad you've used the word symmetry, because it has importance both in the physics and the artistic side of things. I think artists generally have shied away from symmetry. Certainly Henry Moore always said that nothing he did was ever symmetric. He felt symmetry was powerless, yet symmetry is very much a crucial aspect of the unification you've been talking about. And I wondered, Grenville, what you felt about symmetry in your work. Quite a lot of it seemed to be quite symmetric. You're relatively comfortable with the notion, are you?
I think, as I said, because initially I was borrowing or stealing objects, but engineered things that have been taken through several processes. So I was aware that there are multiple objects, like I said, but they're kind of borrowed. So from my point of view, in detail, they were not symmetrical individually, but you'd established a symmetry. And so breaking that symmetry was either using a surface or colour, or very, very fine detail. So it's about the level to which you look at a thing, really, or the degree to which you look.
Yeah, I'm not good, I think, in physics too.
Any further? Yes.
So in science, usually it is, or the big criteria for a good science is that you can actually falsify it.
Yeah.
Now you said somehow, if the Higgs exists, we can accommodate it. If the Higgs doesn't exist, we can't accommodate it. Is there a way of, would there be an experiment which could disprove that string theory is wrong?
Yeah. So the answer is twofold. In principle, yes, very easily. In principle, if we could look at small enough distance scales in nature and look at the string scale, then yes, you would immediately see whether the string's there or not. So that's an in principle answer, that there would be an in principle experiment. Now, practically, you've got to say, can our experimental colleagues do that? And it seems like they can't with current technology. So there's been much made of the fact that using current technology, there are no experiments that verify string theory on that. But I was thinking about it recently in terms of the Higgs. Higgs made his prediction in 1968. And there was no technology around for, whatever it is, 50-something years to confirm the Higgs. And so somehow we weren't worried about, nobody was complaining to Higgs that he's not made a non-falsifiable theory because there wasn't particle accelerators big enough in 1972. So I would say in the current state is we cannot directly test string theory with current accelerator technology. Doesn't mean we won't be able to in the future, but I would suggest that if we do so, it'd be using other things than just banging stuff together. String theory is about quantum gravity. It's going to, the cosmology which is now being explored very deeply and very greater accuracy with current satellites is making more and more detailed measurements of quantum fluctuations in Big Bang, all sorts of stuff like this. So it could be that the future of experimental high-energy physics, in some sense, lies with cosmological measurements, and string theory may have something to say about that. But then I should also add one more thing, which is a theoretical problem. We don't understand the implications of string theory that much yet, which is why we have programs like this. String theory is not a theory that's over that we all understand the implications of, and it's just a matter of testing it. If it was, why would we do research? We'd all be out doing experiments. So there's a theoretical problem, what the actual predictions of string theory are, which is still very open. So yes, it's a theory that is certainly in principle testable. It's taken many years to reach any theoretical understanding of it, and that will continue. And I have faith in my experimental colleagues. They're clever. Just because they can't crank up the energies doesn't mean they'll give up.
I think we have time for one last question.
I'm perhaps slightly naive. I've heard about wave-particle duality.
Yeah.
Anything that's a particle can also be thought of as a wave and vice versa. So if particles become strings, what happens to the waves?
Okay, yeah, so the waves, okay. That's a sort of way of understanding certain probabilistic notions in quantum mechanics, is the wave thing. So actually the strings themselves would also be waves as well. That's a short answer.
I'm trying to visualise a wave.
So maybe I could ask one tiny question myself of you, Grendel. Have you ever been tempted to sculpt something to represent 10 dimensions?
I've got to say that a few months ago I thought there was something like 156 dimensions, and now it's 10.
That's in generalized geometry.
Yeah, I've
Very good.
I've learned how to extend a drawing into several of the dimensions, which is a very different way of drawing to me, and that's not the kind of some of the stuff you've seen in the presentation. Yeah, 10.
One day.
We can manage that.
Brilliant. Well, can I just say thank you very much on behalf of the Institute to both Grenville and David. It's been a fantastic evening, and I hope you've all enjoyed it as much as I have. Many thanks.